All right, good evening. Welcome to week 2. Okay, just a couple things for the announcements to knock them out. First one is make sure that you're turning in your assignments. It's the biggest thing that I see people failing on week 1 of all my classes is people not turning in their assignments or doing the assessments. And the discussions. When you do the discussions, please make sure they're not over 20% copied. I randomly check, but if I see lots of quotes, I will check it. And if it's over the 20%, I'll have you redo it. And I'll give you a couple chances because this is a lower class, one of the beginning classes. Since this is a 100 level class, I'm going to give you guys the chances. And always take advantage of the writing lab, please. It will help you learn to paraphrase. And as you go, you'll learn that paraphrasing is good. Now, the thing about coding, as you know, there's only so many ways to code. So we get used to just quote, quote, quote when we code. We have to remember that that's not acceptable outside of the coding. All right, next thing. Take advantage of resubmitting your assignments. 1, it gives you practice. 2, it gives you higher grades. And we'll discuss the daily checkpoints. You're required to do at least 4 per week. Now, what that does is it gives you 15 points per week, except the final week. Then you get 10 points. So that is 30, 45, 55 points extra that you can get by doing those extra. It's like extra credit. Take advantage of it. That 55 points can make a difference between grades, big time. All right, that being said, let's go ahead and discuss what we're going to be going over tonight and tomorrow. Learning objectives for week 2. Learn about the 3 basic structures in programming: sequence, selection, and loop. Understanding and recognizing the different structures, learning different types of decision statements, and learn about single, dual, multiple, alternative selection statements. Learn about logical and comparison operators. Fun stuff, the basics of all programming right here. No matter what language you're using, these are all the things that take it for you. All right, so something that know some of the terms like unstructured spaghetti code. What it is, unstructured spaghetti codes, basically coding that's hard to follow. And by doing spaghetti code, that's where the difference comes in between those that do it for a living and those that just dabble in it. Spaghetti code has a lot of, it's not as structured. So that it doesn't follow most of the rules that most programmers do. And so a lot of companies don't like that. Because if they can't have somebody step in where you step out, that's a problem. So spaghetti code is logic is hard to follow, prone to errors, which it is. If you're just bouncing around and you don't sit down, spaghetti programmers tend to just sit down and start programming. They have no path. They haven't written anything down like we did in week 1, and you went through, checked the statements. Yeah, that's the opposite of a spaghetti programmer. Difficult to reuse and hard to use as building blocks for larger applications. Because there's no structure, when you start building for bigger applications off of that code, it falls apart. It's just like a brick wall. If the base structure is not solid, the top structure is going to come falling down. It's like building a reverse pyramid. It's going to fall down most of the time. Programs that use spaghetti code logic are unstructured programs that is, they do not follow the rules of structured logic, as I was just saying. Understanding the three basic structures. We have sequence, selection, and loop. All right, let's go ahead. We'll go through this, and then I'll go through and explain it a little more. Sequence is in order. It's like step A, step B, step C. As you can see here, this breaks it down. So it's basically in order. It's, for those of you who have just like Word, Microsoft Word. Let's bring Microsoft Word up. So the sequence structure is basically a layout. So step one, open, let's see, start. Step two, add 1 plus 2. Step 3, add 2 plus 3. Wow, what happened? 1 plus 2. Go away, Siri.
It's 3.
Yeah, Siri's talking to me. She's doing my math. Okay, so now we go add 2, or add step 2. So step 2 plus 3 equals, and stop. As you saw in our coding last week, that's the basic of it, right? So step 1, we start the program. Step 2, add 1 and 2, so that's going to be 3. Step 3, we take the 3 plus 3, so that's 6. Step 4, it equals 6. Step 5, we're finished with the program. So that is a sequence structure. Performs actions or tasks in order, one after the other. No option to branch off and or skip any of the tasks. Selection, and this is a yes/no. It's kind of like, have you ever read a Choose Your Own Adventure book?
No.
No. Do you know what
But I understand what you're talking about.
Okay. So do you know what a Choose Your Own Adventure book is?
Yes.
Okay. A lot of people, there are some people that don't know what they are, so I'll quickly explain a Choose Your Own Adventure book. Okay, so 1, we're going to start. And it helps if I spell correctly. 2, read page 1. 3, choose outcome of page 1 by page 1 with page selections at the bottom of page. So in other words, you read down there, it'll say for this outcome. So let's see. So now what we're going to do, and this is how it goes. For outcome 1, go to page go to page 10. For outcome 2, go to page 15. And each page has something like that to it. All right, and then stop. At the end of the book, you're going to stop after going through so many pages this way. So you choose the outcome, all right? So, also known as a decision structure and if, then, else, okay? So, if I choose outcome 1, I go to page 10. If I choose outcome 2, then I go to page 15. So one of 2 courses of action is taken based on the answer to the question. Begin with a decision symbol. The decision symbol is what we discussed this was. It's not a diamond.
A polyamor or something like that. Or no, I don't remember what it was.
What is
A rhombus.
rhombus? And I intentionally do that because if we're not teaching you guys how to research, and that's why I'll throw this stuff in there, and I'll actually show you how to research it. A lot of it's the basic research, but if I'm not showing you how to research, how can I expect you to research? So that's why I'll sit there and ask questions like that, and sometimes break it down and do it for you. So it's a rhombus, right? All right, so it begins with the decision symbol, which is a rhombus. If I choose step A, the answer is going to be yes. We go to this step. If I choose B, then I go to this step. And then they go to whatever step after that. Sometimes they'll unite. Sometimes they'll just go in different directions. There is no guarantee what these decisions will take you to, okay? So begins with the decision symbol, then branches off. The decision join at the bottom of the structure. They don't, but they don't always join right there, but they will join way down there. Like I said, in fact, what I should do is put another step here, end of book. Now you can see how those actually, now they've joined, right? At the very end. That's the end of the book. The loop. Okay, so it repeats the action as long as the outcome's the same. All right, so, for example, we start. Step 1. If random number is not equal to 10. All right, so, and actually we're going to put the question there. And it is random number equal to 10? All right, so I skipped a step there. Sorry about that. Is random number equal to 10? Yes. Go to and I'm not doing the phonetically correct here because this would be actually small letters and go to is one word in this case for programming. So just know that I'm doing this as the examples here. All right, go to, if it is, go to line 20. No. And we should actually add one here. Select random number. Okay. Select the random number. If not, no. Go to step 2. All right, now, and this will actually go to step 4 if it is. All right, go to step 4. Otherwise, we go back to step 2. Step 2, random 10 equals, so we'll put the print there. Print 10. Now we'll stop. So we've now done our loop, okay? So that's what the loop structure does. Starts with a decision symbol, okay? The rhombus. Welcome back.
Sorry, my internet dropped.
That's okay. We've got some clouds moving in, but not too bad. More of a fire smoke out here.
Oh, no.
Repeat actions while a condition remains true. So, like I said, if random number, while it remains true. So, if the random number equals 10, we go to step 4. If not, we go back to step 2. So this can be written either way. So if yes, then. If no, then. So those are the 3 types of structures: loop, selection, and sequence. All right, so once again, here they are side by side. The sequence, steps 1, takes you to step 2, takes you to step 3, you're finished. Now, what can you think of that would be just like a sequence?
Like any kind of, trying to think, something that every step is exactly the same regardless of what the user is, right? There's no...
So starting a car, step 1, open the door. Step 2, sit in car. Step 3, insert key into ignition. Step 4, turn key. Step 5, car runs. Step 6, leave.
But what happens, I'm sorry, may I ask a question?
Mm-hmm.
Like, what happens in the process where open the door? What if door doesn't open?
Oh, that's when you're getting a little more, that's when we start hitting the selection.
Okay.
Or a loop. Okay. So the basics, open. Well, I didn't say unlock it, did I?
Yes, no.
I just said open door. If it's locked, I just froze the program because in a sequence, there's no allotment for any variance. So I just froze the program. That's a syntax error.
Okay, I get what you're saying. You're basically not going to give them any options except to do one step.
Right.
Okay.
Exactly. Step by step by step. That's what the sequence does.
Okay. But there's no plan for if the steps don't work?
Right.
So does anyone actually use like sequence then structures?
Yes, there are sequences. Because when you print a document, it prints a sequence. It prints it, it does the sequence, right? Step 1, it sends it to the printer. Step 2, print. Step 3, finished.
Yeah, but what happens if it doesn't print? What if it gets stuck in the queue? I know, I'm asking all the what ifs.
Those what ifs with a sequence are what gives us the syntax error, the paper jams, all that. You just basically stopped the program in its tracks until you fix that issue. Then it'll continue with that same process.
Okay.
Now, if I had a selection, if it jams, go to printer 2. Does that make sense?
Yes, it does. I guess yes, it does. I guess I'm thinking like,
You're thinking ahead here,
okay, all
which
right.
is great.
Well,
Most
I'm
people
thinking
do.
maybe like UX terms as a UX designer.
Uh-huh. You're a UX designer, so you think of all this stuff in advance. You've got that practice. And this is what we're trying to get everybody to see is you need to think of this ahead. Okay. Now, I take a selection. Let's do the selection, the if then. So we start to print. Printer one jams.
Wait, I'm
Yes.
sorry. May I pause one more time?
Go ahead.
I'm sorry. I just want to make sure I understand sequence correctly. So it's just, hey, it doesn't work. You got to start at step one again, period.
Or from like, okay, yeah, for example, okay. Step one, sends to printer. Step two, prints. If it's printing at that point and there's a jam, it doesn't go to step three until you unjam the paper or add paper, then it continues on to step three, right?
Yes.
There's no allotment at all. You have to step in. The program doesn't do it.
Okay. Okay.
Has nothing to do with the operator. It's just.
I got you.
Yeah. And
I got you. I got
a sequence, and this is one of those humorous things that we used to have. A sequence does not deal with the ID10T error. The ID10T error.
Is that idiot?
That's idiot. And okay. It's not, I'm not slamming anybody. The sequence is what we call the ID10T error, is if the sequence messed up, you did something wrong as the programmer because, or as you, or there was something wrong with the mechanics. Nothing wrong with the program itself.
Okay. I gotcha.
Okay.
I got you now. It's user error.
Yep. User error most of the time, or it's mechanical error. It has nothing to do with the program error.
I gotcha. Okay. Thank you. I understand now.
That's fine. Now the selection. Okay, the selection. Let's say we have two printers. We have a backup and a primary. If printer one breaks.
I gotcha.
No, then we just print and we finish. If it does, send to printer two, print and finish.
That's built into the program. It's like, hey, printer, that's part of what you're saying, the syntax. If printer one is broken, send this job to the printer two queue. And that's something that the user doesn't have to do. It is done by the program.
Right.
Whereas sequence one, the program never steps in to troubleshoot. It's always the user that has to do the roundabout.
For the most part. That's not always correct, but for the most part.
Okay.
All right, now the loop. All right. I'm going to, how do you eat an elephant? Is the old joke, how do you eat an elephant? It's one bite at a time.
Okay.
All right, so I have the elephant. Do I have more elephant? Yes, I take a bite. Go back. Do I have more elephant? Yes, I take a bite. Go back. Do I have more elephant? Yes, I take another bite. Go back. Do I have more elephant? No, I'm finished. Does that make sense?
Yes.
Okay, those are the things. A loop. It keeps looping until it has that, until it meets a certain criteria.
It's like when someone keeps entering the wrong password.
Yes, except no. Yes and no.
I know you can limit attempts and all of that.
You can limit attempts, yes. Yeah. But like I was saying last week, when we used to, the old passwords with programming, for example, I'm going to use my name as the password. All right, so M1 CHAEL. All right, L. All right, so that's my password. Now, if I did this, M2 by accident, CHAEL, and then realized it? All right, so there's 1, 2, 3, 4, 5, 6, 7, 8, 9, as well as this first one. So that's 10 characters I just typed. So it would not log me in. Now, it only counts the characters that are there. It no longer counts the backspaces.
Yes.
And that's the way it used to do it. So this would be 9 characters. Basically, the password would be, the password that I typed would have been M2CH back 1CHAEL.
Yes, I understand.
Okay. So that's basically what these do. All right. Now, let's say I want to build a peanut butter and jelly sandwich. Which one of these is it?
A sequence.
Are you sure?
Well, I mean, I still am convinced that nothing is a straight sequence, but because, I mean, get bread. What type of bread do you want? I mean, there's all these choices. So
Okay. Well, let's go with what's in the fridge. There's 1 loaf of bread. All right. 1 loaf of bread.
I would say that it's a sequence because you take the bread out and then you...
Not really. That depends on how many people are there.
Okay.
All right. Now we're going to discuss that. All right. So step 1. Step 1 is what? Remember, always,
I would think get the bread first, but that didn't...
always the start.
Mm-hmm.
Now we go to step 2. Because remember, remember how we did this last week? We did the start, and you always have to have an end, because if you leave it open, you get a syntax error, correct? Just like doing HTML. Open, HTML, close. We have to close it, right? Correct?
Yes.
And that's what we have to do here too. So that's where the start comes in. All right, so now we're going to go to, let's use this. There we go. All right, so we start. First step. Well, it depends on the layout of the kitchen. It depends on the individual. But let's go ahead and say, get out knife. Step 2, get out bread. Now, where's the bread?
I don't know.
Oh, that does make a big difference because, well, let's see. First, we will open drawer. Correct? Get out knife. Close drawer. Okay, now, is the bread in a bread box? Is the bread in the fridge? Is the bread in the cupboard? Okay, most people will never store their bread in the cupboard, so we can eliminate that step altogether, right? And this is where we start. If bread is in bread box, open bread box. All right, get out bread. But location of bread. We have to find it, right? By the way, believe it or not, a lot of these steps people will skip. Why do they end up skipping them?
Because they don't have a bread box?
Well, no, you're so used to doing it, you don't even think about doing these steps, did you? You just said get it. You didn't say where. You didn't say go get it. You said get it, right?
Mm-hmm.
So you break those steps down more. All right, and this is one of those leadership questions. The more you go up in a company, you'll start to learn as well. So remember, I told you guys I was going to be teaching you some business stuff as we went because I have my MBA. All right, so as you go up in a company, you're going to have to practice seeing outside the box, and that's what we're doing right now, speak of bread boxes. All right, so if bread is in bread box, that's where we insert this. And I actually, there we go, close bread box. Right? Well, if not, now, if bread is in fridge. All right, so what would be the first step? And we skipped this up above. What can you think of it being?
If bread is in fridge,
Yep.
go to fridge.
Okay. Go to bread box then. All right, so all these steps are going to be basically the same for here, just a little bit different, right? So go to fridge, open fridge, get out bread, close fridge, okay? Now we've gotten the bread, right? So what's the next step?
Locate peanut butter.
Nope, you still have the bread in your hand.
Oh, put bread on the counter.
Open bread. Open bread. Now we go in. Remove needed amount of bread. And here you could actually add another if-then statement. If you take out more, put one back. If you don't take out enough, repeat. See how this is you were correct. This is not a sequence, is it? What one are we doing here? Right now we're doing a selection, right?
Sorry, I was on mute. Yes.
Huh?
Sorry, I was on mute.
That's okay. So right now we're doing a selection, right? Place bread on counter. Or actually, we forgot one other thing before we got the bread. Can you think of what we forgot? And we're not going to go back and write it because you're starting to see the process here.
I mean,
Plate. We didn't get the plate out. We got the knife, but not the plate.
mm-hmm.
So
Do you really need a plate though?
that depends on the individual, doesn't it? Can you see how making a peanut butter and jelly sandwich is not a simple process for a computer, is it?
Well, I guess I guess it can be as simple as, I mean, when we define the process, I guess it's.
But if you're actually defining the process step by step to somebody that doesn't know how to do it, you're still going to write these directions out.
Yes, but the computer also doesn't know that they may or may not need a plate. So do you know what I mean? Like,
okay, somebody brand new on Earth.
I'm sorry?
And they may somebody brand new on Earth. Do they know?
No.
Okay. So if we skip the plate, it's not going to be a factor, but what are they going to do with the bread while they're getting the other stuff out?
Well, we can decide that, I guess. Isn't that?
But remember, we're thinking computer terms now.
We can tell them to put it on the counter. We can tell them to put it on a paper towel. We could tell them to
So in other words, it is a step-by-step process with, there's no actual sequence, like you said. They all come together. You use all of them in a program.
Okay, gotcha.
Now, okay, so now we're going to get a little more complicated here. All right. Guess what we didn't do? While we were in the fridge, why didn't we take out the jelly?
Because maybe it's not in the fridge.
How many people store jelly out of the fridge?
If it's an unopened jar, it's in the pantry.
Good point. So it does depend, doesn't it?
Mm-hmm.
Okay, so now we're going to skip ahead here. So we're going to put ... here, meaning we've now done all these steps. Now we're going to do another step. All right? So up here, when we actually put the bread on the plate, are you going to put the bread down or are you going to put it next to each other? You can actually save a step for the individual when you tell them to place it down on the plate or paper towel or whatever.
Gotcha.
By
Put bread
saying,
side by
place
side.
them side by side. But if you don't, now you have to remove one piece of bread from the other piece of bread and place it by the side. Place them side by side.
You are streamlining the process for them.
Yep. See, and this is how you have to think of this. This is a program. When you're programming a computer, it is step by step. Do you realize us skipping the plate, we just gave it a syntax error because it goes crazy. It will hit that and have a panic attack because what's a plate? Does that make sense? And that's what a syntax error is. It's the program, the computer, having a panic attack, basically. All right, so now we're going to say we have these pieces of bread next to each other. We have the jelly out. We have the peanut butter out. We have the knife. Well, what step did I forget? What's the next step?
Actually making it?
How about opening them?
Oh, okay, yes.
And then picking up the knife. Okay, this is what the ... is. All right, so now I have the knife in my hand. So I'm going to actually put this one, pick up knife. All right, so I pick up the knife. Next step. Place knife into peanut butter. Spread peanut butter onto one piece of bread. What's the next step?
Spreading the jelly.
Maybe.
I mean,
You realize that all depends on the person, right?
yes.
Because,
Go ahead.
Go ahead.
Oh, no, but I'm saying, go ahead. No, go ahead.
Okay. For me, get rid of that. Now I'm going to do this again. All right. Now, saying that again, basically, the reason, I'll show you. Okay. So the reason would be this. Spread peanut butter onto second piece of bread. Because I like my peanut butter on both pieces of bread with jelly in between. So I just threw something in there where this would be a loop. See how that loop is? Because I placed it in the peanut butter, spread it on the bread, place it back into the peanut butter again, Spread it on the second piece of bread. Now I'm going to the next step. See how that is a loop?
Yes.
So basically the loops, see how now all these, like I said, whoops, all these are used together, right? So when you're doing a program, you're going to most likely use at least two, if not all three.
Gotcha. Or that
Yeah.
like each step in a sequence could also have a selection or be a loop or something.
Right, exactly. Now, let's do an assembly line. Do you realize the computer actually just sits there and repeats the same step over and over and over, but step by step by step, so it's a sequence. It's a loop of sequences. For example, put tire on, put bolts on. Go to next car, put tire on, put bolts on, go to next car. So it's kind of a loop, but it's not a loop. It's step-by-step sequence. It's a loop in the fact that it's repeating the same thing, but it's not a loop in the fact that you've now moved another car forward. So there's two parts of the program. One part of the program, pause this car at this point, then move car forward to next car. So the same sequence becomes a loop, but it's not a loop because it's a different. Does that make sense?
Yes.
So now I'm going car B, then car C, then car D. But the same piece of machine is doing a sequence. Tire, bolts, tire, bolts. Or the tire, lug nut, tire, lug nut, tire, lug nut. So that is a loop. But because we're changing cars, it's just a sequence, car 1, car 2, car 3, car 4. So it's a sequence for the conveyor belt, but it's a loop for the machine putting on the tire and the lug nuts. So there's two programs running at once. Does that make sense now?
Yes.
Okay. Now, if anybody has questions on that, please let me know. All right, so importance of structure, clarity. As you just saw, I could make that very confusing if we don't use a structure. Industry standard is the structure so that one programmer could step up and do it when another programmer steps out. Efficiency. Almost all languages enforce structure in their syntax, as you just saw. I just confused you because I said put the plate down, right? But I didn't tell you to get the plate. All right, so combining structures. You can have sequences or tasks followed by a selection or a loop followed by a sequence, as you just saw. Attaching structures end to end is called stacking structures, all right? So this would be stacking structures, for example, would be we're going to start again, right? We always start. Stacking the structure. This is where conveyor belt moves car to robotic arm. Conveyor belt stops at arm. All right, so there it is. There's the process for the conveyor belt, right? And then it repeats. So for the conveyor belt, this end. But we're actually starting again, right? So we ended, to end that one, move car past robot. Tick arm. All right. So there's our loop, right? So now we start again with the next car. So this here is kind of like the stop. So we're going to put the stop right there. All right, now we do this over and over. See how that works? So we've now built structures end-to-end calling stacking structures. See how that stacked the structures? We just repeat them. Now, placing a structure within another structure is called nesting structures. This is where stops at arm. Arm places tire on. Arm places lug nuts on.
So they're like processes within processes.
It's exactly what we just did. Now, because of that, now arm stops. So here, basically, what we're adding now is a stop right there for that one. And then right here, we're actually adding a start. So see how we now have a structure within a structure? Move cars. So this is where we start adding all that. So what I'm going to go back and do, now we're going to copy that. So Command V. See how that's now, we have conveyor belt moves, conveyor belt stops. Now we start the next one. So there's a start, stop to it. This is why we always have a start and a stop. But to the subroutines, we also have a start and a stop. Okay? Does that make sense? See how that works?
Yes.
Okay. These three statements constitute a block or a group of statements that executes as a single unit. And you can see how this is one car having the tire put onto it. That's one way of putting on the tire for that car. Then we go back to the next tire, the next car and tire, then the next car and tire. Okay? So that, see how that works? There. All right, next, structuring and modularizing unstructured logic. Single alternative if or single alternative selection. This is where we get the if-then statements, okay? Now, we're going to say, we're going to add something else into here. Start, we're going to, so this all needs to be moved in one more, because right here now gets moved in as a start. Okay, and stop. But in the middle, start, conveyor belt moves forward to robotic arm. Well, really, is there another car? Now we're going to go in. No. Stop. That's actually going to be out there. Yes. Start. So we come down here, so we have our start and our stop. We have another start. Well, there should be a start right here, right? Because I have an extra stop. So there should be another start here. Start. Is there another car? So all this needs to even go in one more. So you're starting to see how these build down and back out, right? Making decisions. Every decision a computer program makes involves evaluating a Boolean expression. And basically a Boolean expression just means it's true or false. That's all a Boolean expression is. And that's where if yeah, if no, if there's another car, no, it stops. You're finished. Yes, well, we start again. If statement pseudocode standards. Now, this is how we actually do the pseudocoding. If condition, then. Okay? And the if always starts. We always start with an if. We always end that line with a then. If there's another car, then move the cars forward. Else, stop. And if. So in other words, we have the if, and then we have the end if. So the start and the stop. All right? So that's the simplest way to explain all that. Now, relational comparison operators, equivalency operators. If true when operators evaluates as true when its operands are equivalent. So basically, if they're equal, because the assignment operator in many languages is the equal sign, those languages often use a double equal sign as the equivalency operator to avoid confusion with the assignment operator. We're going to go more into that one tomorrow night, okay? And then the greater than operator. We're going to go more into that one as well. Relational comparison operators. Less than, greater than. Less than or equal to. All right, so if I have 10 cars, the belt knows to continue for 10 cars, then stop. If there's less than 10 cars, the belt knows to go that many cars, then stop. If it's less than or equal to 10, then it knows it goes 10 times, right? Does that make sense?
Yes.
Okay. Not equal to operator. If we have no more cars, we end. So there is no more cars. Not equal to a car means no more cars. We stop. So not equal to a number greater than 0. Greater, yeah. So it could be considered not equal to, or you could say equal to 0. See how you could use either one?
Yes.
All right, so let's take a look at this based on what we just went through. Which of the lettered choices is equivalent to the following decision? So these are gonna be the choice, okay? If X is greater than 9, if Y is greater than 9, then output X, and if, and if. So if, and if, and if, output, right? So we do the open, the close. So if X is greater than 9 or Y is greater than 9, then output X. If X is greater than 9 and X is greater than Y, then output X. If Y is greater than X, then output X. If X is greater than 9 and Y is greater than 9, then output X. Which one of those is true based on this?
Hold on, let me think. Um, 1. No, hold on. 4.
Okay, reason?
Because if X or Y is greater than 9, you're always outputting X.
Correct. But it's not an or, it's an and. If that, because the way it's written, it goes in.
Okay,
So
I got
now you have the and. Where if this stayed out here, you'd have an or.
Okay, okay.
And you'd
Yeah.
actually have
Okay,
or
I got
written in there.
totally make it. Sorry, I didn't mean to cut you off. I'm like, okay, totally made a little bit more sense there. Gotcha.
Okay, now let's do another one. In the following pseudocode.
No, no more, no more.
We're almost finished because we're almost
I'm joking. I'm joking.
In the following pseudocode, what percentage raise will an employee in Department 5 receive? If department is greater than 3, raise equals a small raise. Else, if the department is less than 5, a medium raise. Else, the raise equals a big raise. So you're going with Department 5. What will they receive?
Hold on. Let me think. I want to say you don't know.
But you do. Okay. So we start here. If department is less than 3. So less than 3, they don't receive anything based off of this. Based off the information here. Now, the raise is small. That's if it's less than 3. So 2 or lower. Else, less than 5. So 4 or lower is a medium.
Oh, so number 5 is getting 3, a big raise.
A big raise, exactly. And you know what? That was the last one for tonight.
Oh my goodness, thank God I haven't had to do that kind of stuff since I was in high school.
Basically, what are we doing here? Math.
Yeah.
Story problems. So if you can equate a story problem to programming, you're going to catch on. If not, you equate the words to them just like English. Okay? So we equate to either English or math. We'll get the same answer either way. Correct?
Yes.
Okay, so take your strengths and use it. So with that, I know I've blown your mind this time.
No, that makes a good point. In my head, I always think visually. So I would probably, if I wrote it out, I would understand it better. Do you know what I mean? If I actually drew 1, 2, 3, do you know what I mean? If I drew it.
Now, yeah. Let me ask you this. Are you left or right-handed?
I'm right-handed.
You're right-handed. Right-handed people are left-brained, correct?
Well,
left brain.
I agree with that.
Really? Theoretically, yes. Most of the time, the right side of the brain will control the left hand.
But isn't the right side of your brain the creative side of your brain?
Left-handed people are right-brained, yes. They tend to be more creative. Tend to. It's not a hardcore fact. Remember that. Okay?
I'm like...
Then you have people that use both sides, so they become ambidextrous and can see it without writing it out, or they have to actually write it down. Does that make sense now?
Yes. Just, okay. I mean, I think it's probably been a long time for me that I've had to figure out with my visual brain how to solve a numerical math type of a problem.
Yeah. Now you see why I said this class was mostly a lot of theory of how things go.
Our processes.
The process, yeah. It's all, and let's be honest. it is not proven fact. It's just theory with strong indicators of which side of the brain controls which hand. Okay, which means it also controls which one's creative and which one's more process oriented. More creative people have to sit there and write it out so they can see a picture. Process oriented, step by step by step, can do it easier.
Yeah.
But there's no dead set, this is the way it is. But when it comes to programming in a computer, it's dead set, or you get a syntax error.
Yes, gotcha.
Because it doesn't have the other side of the brain to think with.
Yes.
So that's why I brought the brain into it.
No, I get it. It's clicking a little bit more.
Okay.
Like I said,
we'll repeat it more and more and more as we go through the class.
Yes.
All right. That being said, do you have any questions for tonight?
I'm sure I will have a lot of questions tomorrow. I have to process everything first, and then I have questions.
See, without actually writing the program, and that's where I wish that we could do some writing right now, that would help.
Yeah, and I think I have to just break my thought process. Like, I'm so used to thinking of it from the front end perspective. I'm not
all design.
Yes. And typically I just get told, hey, we need something to tell the user what's going on, not, hey, we need to tell the program what's going on. So I just need to kind of break my thought process here from how I'm used to looking at these types of problems, and realize I'm looking at them from the back end, not the front end.
Now, do you also start to see why somebody who could do both front end and back end rather well are in high demand, but not easily found?
No, I do understand that, but I do actually believe you do one or the other better.
I've met people that do both just as well.
Yeah.
So it's a matter of the person's mind. It's not better. They're not better than anybody else. It's just that's their process.
Well, and I agree. I mean, I think anyone can learn both. And it was interesting. I was talking about that in my class today too, that when people say they can do both, I always find that a little questionable, because I think about what makes an effective designer. And you think about how often you work, how long you invest in your career and your education and learning the fundamentals and the tools, the history, the theories of one field. They're two different fields. So unless you're having two full-time jobs doing both, one's always going to be stronger. I mean, I'm sure if I invested the same amount of time, education, studying, research, work into programming, I could do it as well as I do design, but I don't. I only have to dip into coding once every 3-4 months. You know what I mean? Twice a year.
I do. It's the repetitiveness that causes it to stick.
And the experience. Yeah.
Yep.
Yeah.
It's like this. So, all right, that being said, we're going to go ahead and end class for tonight. Thank you for coming to class. I hope you had fun tonight. I know that I gave a lot of information. So, for that, have a nice evening as we end the class.
Thank you, Michael. Have a nice night.